This is content of part 4b. If you're interested only in specific part of this video, just jump to its start time. Now I would like very shortly discuss the observed oscillation, because they are a very important characteristic of nanomagnet. I will discuss about the observed oscillation in more detail in another video, but at this moment I would like to mention that there are several types of observed oscillation. The first type is the oscillation which can be seen during fitting. This one. The second type is oscillation of anisotropy field, and the third type is oscillation of second derivative of the Hall angle. All these oscillations are originated by interface. It is a fact, because the amplitude of this oscillation clearly depends on the nanomagnet's thickness. When the nanomagnet is thicker and the contribution of the interface is smaller, the amplitude of the oscillation is smaller. When the nanomagnet is thinner and the interface contribution becomes larger, the amplitude of oscillation becomes larger as well. The same dependency exists for multi-layer structure. When the number of the layers and therefore the number of interfaces becomes larger, the amplitude of oscillations becomes larger. Next, let's take a look at more details about the oscillation. This is a plot of oscillation at different value of perpendicular magnetic field. Each line color corresponds to a different field. You can see there is a clear pattern of this oscillation. The pattern is even more clear when the data is plotted in a 3D plot. Here you can choose type of your 3D plot, and next just push this button, plot 3D. You can adjust view of your plot by pushing middle mouse. This looks fine. The existence of pattern is very clear. There are minimum and maximum lines at specific angle. The pattern repeats itself from nanomagnet to nanomagnet, from a wafer to wafer, with a different angle between lines and with some additional features. So first question is, why is it important measurement? These lines are very important measured features because these lines correspond to some features of orbitals of atom at the interface of nanomagnet. For this measurement data we can clarify the orbital's shape at the interface, also called the surface reconstruction. And the second question is, how can it be proved? Firstly, the intensity of these lines increases for thinner nanomagnet, which is clearly indicates that this feature is originated at interface. Secondly, the line shows that there is some enhancement or change of spin-orbit interaction at some specific angle of applied magnetic field with respect to the orbital symmetry axis. This is a strong hint that is a feature of the spin-orbit interaction. I already have explained that the magnetic field of spin-orbit interaction is always parallel to the applied external magnetic field. The spin-orbit field is largest when the magnetic field is applied along the largest orbital deformation. Or the same fact in the different words. The strength of spin-orbit interaction depends on the angle between the applied magnetic field and the axis of orbital symmetry, or the axis of orbital deformation. Once again, I will explain what is plotted here and why the lines are important. One axis, this HX, is in plane magnetic field. Another axis at Z is perpendicular to plane magnetic field. Both fields are apply external magnetic field. The plot data is the value which is proportional to the anisotropy field and therefore to the coefficient of spin-orbit interaction. The lines mean that the peak of spin-orbit interaction is at a specific angle of the magnetic field. The shape of the peak value are lines, not radius, not dots, but lines, which means the specific angle of applied external magnetic field. That is exactly what we expect from spin-orbit interaction. Once again, what exactly the value is plotted here? Let me remind you that it is important linear relation between the measured in plane component of magnetization and applied in plane external magnetic field. From this relation, the anisotropy field is evaluated. This relation is linear only because the relation between magnetic field of spin-orbit interaction and external magnetic field is linear. When this relation does not hold, this relation becomes nonlinear as well. Rotation of external magnetic field is such a case. So in this case, the proportionality coefficient or coefficient of spin-orbit interaction are different when for different direction of the applied external magnetic field, it is because of deformation of orbital. Once again, I want to review how we measure these lines and why these lines correspond to peaks of coefficient of spin-orbit interactions. And we measure experimentally dependence of in-plane component of magnetization versus in-plane applied magnetic field. The dependence is rather linear, but there is some oscillation on top of it. So we subtract the raw data, measured data, and linear fit. As a result, we see these more clear oscillations. So we plot this oscillation on 3D graph, which shows how the measured data different from expected linear dependence, and therefore how the anisotropy field depend on the angle of applied magnetic field, and therefore how the coefficient of spin-orbit interaction depend on the angle of applied magnetic field. Next step is analyzing of fitting data. For this we need to use another program, and we will use these 4 files of calculated anisotropy field and offset field. So remember, we can find these 4 files which all started with all. It could be only 2 files in the case when the scan was only for one direction. In this case, 2 directions, 0 degree, 90 degree, along current and perpendicular current. For this purpose, you need to start another program with name few-many anisotropy new 2. Again, you have 2 options, executable file or LabVIEW file. So I will start LabVIEW file. When you start the program, you can see many graphs. I will explain each of them. But first, I will explain how to load the data into the program. Go to the folder containing all data files, and we will load only these 4 data files for anisotropy field and offset field. Copy directory name, paste here. These indicators show that the file for anisotropy field and offset field exists in the directory for specific scan, 0 degree, 90 degree. Next, press read all. The program loads the data for anisotropy and offset field. That's all. These 4 graphs, 1, 2, 3, 4, are direct plots of the data of these downloaded files. This is an anisotropy field as function of perpendicular magnetic field for 0 and 90-degree scans. This is offset field for 0 and 90-degree scans. The lines of different color corresponds to a measurement at different current density. The data can be independently checked by another plotting program. For example, just drag the data for the anisotropy field into the origin. For example, this one. And plot the data either for one specific current, for example, this one, or for all currents simultaneously. You can see there is a one-to-one correspondence of this graph and this graph. Similarly, you can check the graph for offset field. For example, let's check for perpendicular field, such as perpendicular is this one offset, that was Hani offset. Drag here. So there's a one-to-one correspondence to this graph. The data in numbers for each data file are shown in these tables below. The upper row is the current. The left column is the perpendicular field. These numbers are value of anisotropy field, and that is therefore values of offset field. It is important to notice that anisotropy field is nearly exactly the same for 2 scans, as it is expected to be. In contrast, as offset field is very different for 2 scans, along and perpendicular to the current. If you are interested to see the content and other parts of this video, you can find the links below this video.